Okay, in this segment we're going to start talking about a class of circuits which is near and dear to my heart called translinear circuits. This is a family of circuits, and the word translinear is one that was coined by Barry Gilbert in 1975. So, and he meant it in, he's actually the one who invented this class of circuits. He was a very, very famous analog circuit designer who, back in the late 60s, was working for Tektronix in Beaverton, Oregon, on the west coast near Portland. And he had done some work with analog devices, and analog devices liked him so much that they wanted to hire him. And of course, analog devices is based around here in Massachusetts. And so Barry said, well, I'm not interested in moving away from the west coast. He really liked it in the Pacific Northwest. And Analog Devices basically said, okay, you can stay out there. And they basically opened the Northwest Design Center in order to have Barry Gilbert work for them. And so he did, and that design center still works, is functioning today. It turns out Barry Gilbert just died this past, I guess it might have been January 30th of this year. He slipped and fell in his home, and he died. I'd only learned about that about a month ago, which is very sad. But he was probably one of the greatest living analog circuit designers in the world. And this class of circuits is his brainchild. But anyway, so this word translinear, he meant it in a couple of different senses. The first is a contraction of the phrase transconductance is linear with the current. So translinear. And so we've met the transconductance gain before. Transconductance gain of a bipolar transistor is equal to DIC dVB, as we've defined it. And of course, IC is equal to IS e to the VBE, VB minus VE, that is, over UT in the forward active mode. And so GM would be d by dVB of IS e to the VB minus VE over UT. And that's, of course, just the derivative of an exponential is just the exponential, so we get IS e to the VB minus VE over UT. And we apply the chain rule and take the derivative of the argument of the exponential with respect to VB, and that brings down a 1 over UT. And so this, of course, here is just the collector current IC, and so this is just IC over UT. This is something that you probably found on pre-lab 3. And so the transconductance gain of the device is linearly related to the collector current. And that's a hallmark of all devices that have an exponential current voltage characteristic. So it's just another way of saying that the device has an exponential current voltage relationship. I want to show you some measured characteristics that I took a while back. So this is a Gummel plot of a bipolar transistor, much like the ones you'll be doing for Lab 3 Experiment 1. Only this is a different type of transistor. You're using a 2N3904. This was one of 4 transistors on a very nice transistor array made by Analog Devices called a MAT14. And these are some of the nicest bipolar transistors you'll ever see. They have a very, very nice, almost ideal exponential characteristic over many, many decades of current. Here goes from 1 nanoamp up to 10 milliamps without any sort of real sign of bending over. And you can see that the base current is also following a nice exponential. These are very nice, nicely parallel to each other. And you can see that these lines are actually quite far apart. And if you go over here and you look and see, how far apart is 2 orders of magnitude, these are well over 2 orders of magnitude distant from each other in the vertical dimension. In fact, this is the collector characteristic fit with the parameters. IS is 105 femtoamps and UT is nearly the ideal value, 25.6 millivolts. And if you simply just take this fit and divide it by a constant 679, you wind up with this line here for the base current. So you can see it's a very nice fit, very constant beta, and it's a very high beta. So the beta of these devices is typically in the 600 to 1,000 range, which is really, really good. If we take the collector characteristic here and we numerically differentiate it, much as you'll be doing in experiment 1 of lab 3, to get the transconductance gain, if we plot it as a function of the collector current, we get a very, very nice straight line relationship here. This has a slope of 1, and indicating a power law of 1, a direct proportion, and the slope of this black line that's superimposed in the data points is the value of UT that's consistent with the fit from the collector characteristic on the Gummel plot, and it's just really, really pretty. There are very few times when you actually get measured data to line up with a theory for a nonlinear device this well. So anyway, the BJT, especially these guys, are very, 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 very nice, ideal transistors over many decades of current. And so this first sense of the word translinear that Barry Gilbert had in mind is this effectively description of the exponential IV characteristic. The second sense of the word is sort of he meant it to convey the notion of a bridge from the world or from the familiar territory of linear circuit design to the uncharted territory of nonlinear circuit design. So a bridge, sort of like trans, using the word trans in the sense of a cross, a trans from linear circuit design to nonlinear circuit design. So we can say a lot of very general things about linear circuit design, and we can say relatively few things in general about nonlinear circuit design, other than we can't say very much about it in general. Everything is a special case, and in many cases the math is not very tractable. But with translinear circuits, it turns out that they do admit a very high-level type of synthesis, and that's a subject that we'll not be getting into in this class, but I have taught a whole semester's course in my previous incarnation as a professor at Cornell, graduate level course on translinear circuits and translinear circuit design. So it is a vast subject that we will only be sort of scratching the surface of this week in this class. But there's also a third sense of the word, which Gilbert didn't really bring out. But as we'll see, the translinear principle, which we'll get to in a little while here, is a translation of a linear constraint into a nonlinear constraint through this exponential IV relationship. And we'll see what that means here in a little while. Okay, so what we're going to do is consider a 4-transistor loop, so translinear loop. This marker is somewhat tired, so let's consider the following so-called translinear loop. Involving 4 transistors. So we're going to have 4 NPN transistors. And these 4 transistors have collector currents that we will number I1, I2, I3, and I4. And we're going to number their base emitter voltages by V1, V2, V3, and V4. And we have a closed loop of base emitter junctions. So we have this loop in the circuit that goes like that. And I should say a couple things here. First of all, we are not showing everything in the circuit. Like we considered the pair of transistors in the current mirror initially. We weren't showing what these things were connected to. So we're presuming that the collectors of each of these transistors are connected to other points in the circuit, and that the bases and emitters are connected to other points in the circuit. So the currents can flow in and from places that aren't shown and to places that aren't shown. We're just sort of taking this loop out of the circuit and considering it by itself as a piece of a circuit. And so we'll see some examples of actual translinear circuits with the fuller context. But we want to emphasize at this point that these are not open-circuited collectors. These are not open-circuited bases. There's a place for current to flow into and out of from these places indicated by these little stubs here. And we're just considering this 4-transistor loop. And we're going to assume our standard things. We're going to assume transistors are matched. Same temp. We're going to assume idealized. Transistors, which we're going to take to be basically beta going to infinity and the early voltage being negligible, BVA going to infinity. And we're going to further assume that all 4 transistors are well described by the forward active model. So they are either in SAW saturation or they are in the forward active mode. Okay? And what we want to do is we want to say, well, what can we say about these transistors on the basis of this? And what can we say about the relationship that holds between these collector currents, I1 through I4? Well, we know for each of the transistors something about the IV relationship based on the third assumption, namely that I sub I is equal to some IS parameter times e to the v sub I over ut. So that's the forward active model. And we can invert this relationship and solve for vi. So if we take is downstairs underneath the I sub I, we take the log of both sides, and then we multiply both sides by ut, we can find that this means that vi is equal to ut times the natural log of I sub I divided by is. Okay, so that's just taking the IV relationship and inverting it to find an VI relationship. And we also know KVL, right? So we can write KVL around this loop. KVL holds for nonlinear circuits just as much as it holds for linear circuits, and so KVL tells us that the sum of the voltage rises is equal to the sum of the voltage drops. And so we have here V1 as a voltage rise as we go around this way. We see the minus sign first. V2 is again a voltage rise. We go from emitter to base. And then when we get to V3, we see V3 as a voltage drop. We see the plus sign first and then the minus sign, and then we encounter the plus sign for V4. So we have KVL telling us that V1 plus V2 is equal to V3 plus V4. And of course, right away we can substitute in here VI for each of these 4 voltages. So we can put in for V1 ut times the natural log of I1 over IS plus ut times the natural log of I2 over IS is equal to ut times the log of I3 over IS plus ut times the log of I4 over IS. Okay, so we made some further assumptions, i.e. Here that they are operating at the same temperature, which would be true if they're integrated together on the same integrated circuit, the same chip. And so if they're at the same temperature, the UTs will cancel because every term here in this equation is proportional to UT, or has got a UT factor. And so we're left with the log of I1 over IS plus the log of I2 over IS is equal to the log of I3 over IS plus the log of I4 over IS. Now there is a property of logarithms which says that you can take the sum of logs and write that as the log of the products. And so by doing that, we have that the log of I1, I2 over IS squared is equal to the log of I3, I4 over IS squared. Well, we can exponentiate both sides of this equation, or take the anti-log of both sides, and find that this implies that I1, I2 over IS squared is equal to I3, I4 over IS squared. Well, it's the same value of IS because the transistors are matched. So each transistor has its own IS, but they are matched devices, so they should have the same IS parameter. And so we can cancel that from both sides of the equation. And we are left with a very simple equation, I1, I2 equals I3, I4. And this equation involving the product of the collector currents in the transistors that we met as voltage rises is equal to the product of the collector currents whose base emitter voltages we met as voltage drops. And in this pithy little statement here is what Barry Gilbert called the translinear principle. Which is typically abbreviated TLP. And it basically goes in general that in a closed loop comprising an equal number of clockwise facing and counterclockwise facing base emitter junctions, the product of the clockwise currents is equal to the product of the counterclockwise currents. Okay? So you can divide up these transistors here, these BJTs, into two classes. The class that you meet emitter first, i.e. when you go around the loop, you'll meet the emitter before you meet the base, and those would be, let's say, if we're going around the loop in the clockwise direction, those would be the counterclockwise devices, because the emitter arrow is going in the opposite direction. It's going in the anti-clockwise direction or counterclockwise direction. And then we have the other devices, which we meet base first and emitter second, and those have the emitter arrow facing in the clockwise direction. So those would be the clockwise currents. So the product of the clockwise currents is equal to the product of the counterclockwise currents. The names clockwise and counterclockwise, actually anti-clockwise is what Gilbert used because that's how they talk in Britain, and he was a British gentleman, are just arbitrary names. We could call them different things, but that's what Barry Gilbert decided to call them, and so that's what they have been called. But you can see here that KVL, which is where we started, and it's not just any KVL expression or any KVL around any old loop. It's KVL around a closed loop of base comprising just base emitter drops. That's a linear constraint on the base emitter voltages. And what we did here through this derivation was we translated that linear constraint into a multiplicative constraint, a nonlinear constraint, through the logarithmic VI relationship of the translinear devices. So that's a third sense of the word translinear that I think is applicable in this case. So you can do a more general derivation of this involving n transistors facing in each direction, and come up with a statement using the pi symbol for products where you index from 1 to n and stuff like that. But for our purposes here, this will be good enough. So we're going to look at some specific examples of this particular translinear loop embedded in an actual circuit context. And we'll see even with this one loop of transistors, we can do several interesting examples of this. So one thing that people sometimes ask is, well, what would happen? There's no law of nature that says I can't take 3 transistors and connect them up in a 3 transistor translinear loop. Why do I need the same number of transistors facing in the clockwise direction as I have in the counterclockwise direction? So why couldn't I, or what would happen if I took transistor 4 out of my loop and I just simply shorted, let's say, these 2 points together? I still have a closed loop, right? And I still have the ability to write KVL. Well, what would happen in our derivation? Well, we would eliminate this one, that term, right? That would get rid of this term. That would mean that we would have just that one term on the right-hand side. And that means what we would have going on here is that when we went to cancel the IS's, we've got 2 of them over here, and only one of them over here. And so we could cancel one of them, but we're left with an extra IS. And so what happens is that the translinear principle, we could call this maybe the translinear principle prime, now involves the product of, let's say, the counterclockwise currents here is equal to the product of currents, but here we have only one clockwise facing current, and we wind up with an IS that's left over. And so, see, this expression, this translinear principle expression, involves a product of things that have units, like currents. So the units over here are amps squared. And if I only had one current over here, I would have a product that would have units of amps. And I can't have amps squared being equal to amps. That just doesn't work. And so what happens is the math works out so that we actually have another current over here that preserves the amp squared units. And the current that does that is the saturation current of the BJT. And so, whereas the original translinear principle, where we had an even number of transistors, half of them facing one direction, half of them facing the other direction, we had a constraint equation that only related to the collector currents. It didn't relate to any device parameters. There was no temperature dependence. It was just purely a constraint equation involving the currents flowing in the devices. Whereas in this particular translinear principle, this aberrant translinear principle, we now have an IS, and this IS parameter is not only a device parameter, which is a really, really small current, it's like 100 femtoamps or something like that. It's also exquisitely temperature dependent, and so our constraint equation now has this very, very steep temperature dependence, which will make this anything that relies on that particular value subject to variation as the temperature changes in the room, by like 100% for every 10 degrees change in the temperature. And so it's very desirable to structure or impose a discipline on our circuit design so that we have an equal number of clockwise facing transistors as we have counterclockwise facing transistors. Okay, that's a discipline that we impose on our loops of transistors in the design process so that we have this very nice property of not having any sort of device parameters or temperature dependence in the constraint equation that we're working with. Okay, so that's it for this segment, and in the next segment we'll start to consider some examples of that 4-transistor translinear loop in action in the context of an actual circuit.